So welcome everyone to our meeting in the DYNAmore Express series. And today Willem will give us an introduction on how to do topology optimization. And he's going to apply this to the automotive hood and to trying to optimize the structure of the automotive hood related to a couple of different load cases. And yeah, like usual, if you have questions, please post the questions in the chat, and we collect them and trying to answer them afterwards if there are some questions. And please keep in mind that there's some delay in the live stream, so please do not send a message right at the end, but just at the moment you have the question, just post them in the chat, and then we're going to check and try to answer them later. Okay, with that being said, Willem, you may take over.
Okay, thank you. Okay, good afternoon or good morning, everybody. So this is the talk about using LS-TaSC for the topology optimization of automotive wood. We will be digging into several topics, firstly some theory, and then how to do the multidisciplinary optimization of this wood, designing it for NVH, statics, and crash. And then we're going to go to the design code. That's the pedestrian impact. That's the NCAP code. And we're with all of those multiple load cases, and we'll be doing a worst case design study to solve it for all of those many design load cases in the code. So I'm Willem Roux, I'm the speaker here. Most of the work was actually done by Imtiaz Gandikota. And Gullian Yi also helped us. She's mostly responsible for the linear and NVH topics. Okay, so in general, what I'm going to discuss here is the design requirements from the clients, how the market or the automotive companies got us here. Then I'm going to dig a bit briefly into the theory behind the multidisciplinary topology optimization. And then I'm going to do the actual topic, talk about this optimization of automotive hood. So the design requirements, how did we get into all of this work? This work mainly started from the crash groups at the various automotive customers. That's like Toyota, Mazda, Ford, General Motors, etc. So they initially wanted us to do topology optimization for impact and crash and the like, which is a very different topic. That's why they came to us, because there's stuff like maximization of energy in the head impact criterion, which is very specific to what we're doing. For example, in general, if you do topology optimization, you want a structure with the minimum energy, because a structure our structure works is to support the load, and a better structure does less work supporting that load. But that's very different from what you would see in crash, where you want to have the maximum energy absorption. So we had to solve all of these, and eventually we became the specialist in crash and very good at it. But added to that, we had to do multidisciplinary design optimization. The thing is, a part is not only used for crash only. It's mainly used for statics and NVH, but you have to design it for crash as well for safety. So in order to design this part, you have to design it for crash, statics, and NVH to have the optimum part. So that's how we got into multidisciplinary design optimization. And then it was also adopted for many other uses. But all of this resulted in a methodology and successes and insights that are unique to what we're doing with LS-TaSC over in Ansys at Livermore. Also going to go into the theory, but just the overview. There's some stuff that's very interesting and particular to what we're doing in LS-TaSC. The main thing is that we have to design for a saddle point problem. That means we've actually got two design problems rolled into one. So this goes back to what I was saying about the energy. Normally, to have a structure, you would design for the structure with the minimum energy state. But if you're doing crash analysis, issues like having the maximum energy becomes important, and you cannot design for that directly. A structure with the maximum energy absorption would be kind of unstable. I mean, typically you get your maximum energy at infinite displacements and stuff like that. So you have to have special methods to get actual working structure from from your problem statement. So what we're doing there is we're solving this saddle point problem. Like I said, this is where we've basically got answering two design questions. So what we have there is we've got the standard set of variables for topology optimization, where we say minimize the energy to get a stable structure, and then we introduce a different set of variables to control the energy absorption characteristics of the structure. So we've got this dual problem going on, and this is pretty unique to what we're doing, but we found that this is useful for many other things, because suddenly it's much more natural to do normal stuff like minimizing the mass of the structure and so on. Everything makes a lot more sense once you've got this concept mastered. So this went into a lot of the other methodology as well, specifically that's known as the design sensitivity analysis. Now that's a long name for a straightforward concept. What this design sensitivity analysis is it tells you if you change a variable, how much does your response change? So for example, if you want to decrease the displacements, what changes should you make to the variables? That's what this design sensitivity analysis tells you, and it's obviously very important. So historically and typically, this was for topology optimization. This is done using analytical DSA, where you just get the formula and you implement it into the finite element solver, and then you use that for in your optimization. Unfortunately, this is not practical for crash optimization to implement it into the code. It will run too long. It will create many problems. So there is an alternative methodology. This is what's actually being used in LS-Opt and OptiSlang. That's this using a multi-point method. Historically, that was not thought to be possible for topology optimization, but we figured out how to do that, and we're using that to create to handle the constraints for the crash discipline, like maximum energy absorption or injury criteria. So inside the code, we've got both of these implemented, and both of these are used simultaneously in the multidisciplinary topology optimization. So this is methodology that are unique to what we're doing. So this also carries over into the optimization method that we're using. Once again, like I said, you're basically solving two problems simultaneously. You're joining two problems to make your one design problem. Once again, like I said, in one saddle direction, you use the normal topology optimization that you would find in the standard textbooks and competitive codes. And in the other direction, we use parametric variables like you would find in the parametric codes like LS-Opt, etc. I've got a reference at the bottom containing the theory. That's that article on computer methods and applied mechanics. Okay, so let's move on to what we actually want. I think everybody actually want to hear about is how we do this hood topology optimization. This is a study we got a couple of years ago from Jaguar Land Rover, but it seems to be important for all of the automotive customers. So what I'm showing in the first slide is just designing it for free static load cases. Let's start with the statics first. So on the left there, we're showing the structure that we're designing. So there's the outer skin of shells, and inside that there's a solid structure within which we will find the optimum topology. And this is subject to three load cases: that beam load case, a torsion load case, and a bending load case. So we're designing for these three load cases to find the optimum topology. And that's just the design history, how the optimal design evolved. It's shown over there as well. At the bottom right, in that colorful plot, we're showing the design contribution plot. What that plot does is it tells you which part of the structure is being used for which load case. So that green part of the structure is being used for the torsion load case, while the red part of the structure is useful for the bending load case. So the next design study is just showing how this will work for impact. So this is just one simple impact, just to get some basics of what we're doing in the hood design started. So the actual dyna analysis is being shown there. So that's the impact of that head impactor on the hood. This simulates when the car hits a pedestrian and the head of the pedestrian hits the hood. In that case, we're worried about the damage to the head, specifically the damage to the brain. So the brain damage becomes a constraint known as HIC. HIC stands for Head Impact Criterion. We show that in the history plot there at the bottom. So that red line in that history plot is the acceleration of inside the head. And that green window there, we move around to find the time of maximum damage to the brain. And once we've found the time of the maximum damage to the brain, we take the average value, and that's then this injury criteria. It's obviously very nonlinear, tricky to compute, and it's a good thing we have these multi-point methods, because they can actually compute the standard. The standard methods in the handbooks will not do well at this kind of constraint, but the methods we have, that's okay on this. So in the center there, I showed the optimization problem description. So we minimize the mass at the same time as maximizing the stiffness. So having the maximum stiffness is just your definition of having a structure. So the maximum stiffness just tells we want to have a structure, and we want to have the minimum mass of this structure. And on top of that, we've got these other constraints. The HIC value must be less than 1,000. And then we've got this a displacement into the hood. That is just from preventing the person's head hitting the engine block. So you cannot deflect so much that you would hit the engine block. So that's what that Z displacement constraint does. And if you do the topology optimization of this, you get that structure shown there. So this is all very interesting. It shows that we can do these studies for impact, but to design a hood, this is not yet enough. So for the rest of the talk, I'll work through the rest of the stuff that's required to design a hood. Firstly, going into multidisciplinary topology optimization, and then later the design code. So this part is where we're looking, just showing how we can do multidisciplinary topology optimization. So the disciplines required here is the impact, that head impact, statics, like I've shown before, and NVH, like the fundamental frequency. So we've got, in this case, just 3 of those load cases. And there's the design problem. Once again, we want the structure with the minimum mass. And the constraints is once again the HIC and the displacement, the penetration into the hood. And then from the other 2 load cases, we've got a torsional displacement constraint from the torsional static load case. And we've got the bending frequency constraint from the NVH load case. And if we design for that, we get the structure shown at the bottom. And this is the design contribution plot showing where the different load cases are active. So what this plot tells me is at the bottom of the structure, there's a shell being created to drive up the bending frequency. You have to spend some time with these plots to understand how to use them. Just some more results. Okay, that's the history. The animation is how the history is created. And these other plots are the histories of the different constraints, the constraint value versus the design iteration. So this is the head impact criterion. So in the beginning, it's unfeasible, but it's feasible later. This is the intrusion into the hood, how close it gets to the engine block. And as you can see, this one is always active for this specific displacement is satisfied. The bending frequency, characteristic of the bending frequency is those jumps you see there. This is when the dominant mode jumps from one mode to another one. This is very, we always see this in topology optimization. It's characteristic of this work, and we've got special methodologies addressing this, but that's not part of this talk today. So right now we're moving on to the design code. The design code that's being used here is the Aero NCAP pedestrian testing protocol. On the left, we show a figure explaining that. So you have to do that head impact test at many, many places. In fact, you have to do it in 2 test zones with different criteria active in the 2 test zones. But then within each test zone, you have to test at all of these locations. So if you do this as a design study, it's going to become a multi-case design study with many, many, many cases. So this is going to be very expensive to do. So what I'm showing here is doing the design study just for 5 cases. So that's what's shown there, the 5 cases in this design study. That's probably the different locations of the head impactor. And we do topology optimization for those 5 cases with the HIC for the one test zone less than 1,000 and HIC for the other test zone less than 2,000 and the intrusion less than 100 millimeter. And that gives those 2 topologies shown over there. But the point I want to make is this is very expensive. As you can see, that's like 500 LS-TaSC. So we started looking at worst case design studies to reduce that number of DYNAmore. I mean, right now we've got 5 load cases. It ends up that we've got 5 load cases here. In general, you need many more, but it ended up, it looks like you can get away with only 3 load cases in these topology optimization studies. That still have to be verified though. Okay, so this is how we're going to do the worst case design. So what we're going to do in the worst case design is we're going to find one load case that if we design for that load case, all of the other load cases are satisfied. So if we can find such one load case, then we only have to design for that one. But the problem now becomes finding that load case. That's what we're doing in this slide. So as what's shown here at the right is all of these locations where the head impactor can hit. So we do a design study at each of them. And then looking at these design studies, we found out for which one of these cases we must design. So what's shown here is the result of all of these design studies. So the structure shown there is not the actual structure. That's an overlay of all of these structures from the design studies. So each design study is impacted like that. And in the background, we show all of the designs we get. So that's an overlay of all of the design studies. And the color shown there is the head impact value. And as you can see, this one is the worst case. That's the worst case head impact scenario that we have. And over there, we would just explain how these design studies are done, each individual design study. So for each individual design, we minimize the mass subject to a maximum intrusion. And then we look at the HIC values. The HIC values obviously differ. And as I said, that's the worst case design. We're going to use that for the worst case design study. So the next slide is how we did this worst case design study. So right now, we're going to use 2 load cases to do the worst case design. The one shown on top is a load that represents all of the locations. So it's basically a uniform load all across the hood. There's a load at every possible impact location. So we're designing a structure that will support the load for all of the load cases. And then the second one, the one below, is the worst case design. If we satisfy the constraint for that design, then the constraint will be satisfied for all of the load cases. So that's how this worst case design works. And okay, setting it up is a bit more complex. But anyways, we find the structure at the bottom there. That's now the optimum design for this worst case design study. Shown the histories are this, that's the displacement constraint. As you can see, it starts infeasible and then it becomes feasible. The HICs, same thing, it starts infeasible and it becomes infeasible. We're actually still doing some more work here, both us and industry. Many people are interested in this. So one of the studies we did after that is just making sure that this worst case design study actually worked. So we went back and tested the optimal design at many locations just to see that it's true that if we design for that load case, or the other load case is satisfied. So that's what we're doing here. We're evaluating at many different locations. The locations are not symmetric. That's why these values differ. So on the left are the HIC values. And if you look at the HIC values, you can see, yes, indeed, the worst case, the HIC values are satisfied for all of these. On the right, however, are the displacement intrusion constraint, and from that you can see the one is not satisfied. So what that tells us is we need to introduce yet another constraint to satisfy that displacement constraint. So this was kind of expected, nothing new here. So we basically may have to iterate a bit to do these worst case design studies, unlike linear, but I think we actually should have known from the start that we need that extra load case for the displacement. Anyway, this is ongoing work and it's very encouraging. I mean, this methodology, from what we've seen here, it seems to be a viable methodology. Okay, different topic, but very important to everybody. The question here is, now I've got a design from LS-TaSC, but how do I get this design back to CAD? How do I get my CAD geometry from the LS-TaSC geometry? Now, in general, what we know about of what we use, what we see and use, there are two ways. The one is space claim distributed by Ansys, by us, and then there's ANSA distributed by Beta CAE. I think everybody is familiar with both products. So shown here is some results that we got back from ANSA, where they took our design study 1 and converted that into a solid structure. And in general, though, you may want to use a shell structure. So we also got a different study from them where they took solid LS-TaSC design and converted it into a shell structure. So the structure shown in the background is LS-TaSC design. They used 4 impact load cases, and they got that specific LS-TaSC design. And then they created this shell structure on top of that LS-TaSC design. So this was all done by Beta using ANSA. So this is not done by us, but still I think everybody here would like to know about this. Okay, just to summarize what we were doing here. So this was a very interesting and quite a fun study to do. I think it's a very big step forward in terms of what we could do for topology optimization. So what I've shown here is firstly that we can do these studies for impact, in which we already become very well known for, but that on its own was a great step forward, but that happened some time ago. But to that we started adding this multidisciplinary topology optimization, which is actually important to have a practical design, because you have to design for statics, NVH, and impact on this at the same time in a practical design loop. And in addition to that, you also have to pull in these design codes, like this NCAP design code that we considered here with those many load cases. And to handle that, we also proposed this worst case design study, which actually worked out quite well. And the whole of this, all of these together, becomes a practical industrial application and use of topology optimization to solve for hard design problems. We also discussed the theory briefly, but I think the important thing is that we can use these for difficult industrial problems. So altogether, I think this is a new level of maturity for topology optimization. Okay, thanks everybody. If there's questions, we'll be hanging around.
Okay, thank you, Willem. My colleague just informed me that a few people had problem with access to URL, so that's missed part of the video. But for everyone who missed now parts of the video, we recorded the video and we will be online on our YouTube channel soon. So just in case you missed something, no problem. Okay, so there are no questions. I'm just wondering. What's the next step of the LS-TaSC development? Do you have some kind of projects you're working on which will be released soon, or how's the timeline, or what do you plan to do?
Okay, so we're working in several areas. What I've shown here is just a topology optimization. There's also shape of shells. We're looking into that, and there's also thickness of shells. So we've moved, as I've shown there. I mean, you can once you've got the topology, you move it to a shell structure, and then we start designing that shell structure. So there's quite a bit of work being done on shell structures. So you can also do this root example as a shell thickness problem. So we're going to dig a bit into doing that, and then you can also do it as a shape design of shells problem. So we're also digging into that. That's going to be coming available over the next couple of years.
And what about the isogeometric analysis? Is it like you can use it right away, or do you need to do implementations, or is it already working? Because I heard that a lot of people now, there are some people are trying to use also isogeometric analysis. Is there something also related to this for the topology optimization?
We will eventually get to isogeometric elements, but for us, it's more of an element type. So we have to get the methodology working, and then we can just change around the element types.
Okay, so it's more into the future, so to say. It's not so close then. Yeah, okay, anyway.
Yeah, it's not so close yet because of the design sensitivity analysis and.
Okay. Okay. So there are no more questions. So with that, I'm going to close the stream. And again, for the ones who missed it, missed parts of it, I'm sorry. But the video will be online on the YouTube channel soon. So anyway, thank you for everyone else. Also, thank you for you, Willem, for giving the talk, giving us an introduction or a little overview about LS-TaSC optimization. And with that being said, thank you for your attention and see you next time. Bye-bye. Bye.
Thanks. Bye, everybody.